Welcome to another installment of the Robinson Twins present Earth is Our Spherical Home Planet. We've had videos in the past about proving the Earth's rotation using Foucault's pendulum, which was done in 1851. But Foucault wasn't done yet. He thought we could not only prove the Earth was rotating, but measure it more precisely. So in 1852, he came out with the Foucault gyroscope. In fact, he's the scientist who first used the term gyroscope that we still use today. And the mechanical gyroscope was used for decades, and it's still used. But there were advancements in the 20th century in microelectronics and in optics that allowed for even more precise and more reliable gyroscopes that don't have any moving parts. And in the micro department, you actually have a smartphone gyroscope that you're carrying around with you, especially if you play games where you have to tilt your phone to steer or maneuver. That's being done with the gyroscope. After the Michelson-Morley experiment failed to find the luminiferous ether, a lot of scientists weren't prepared to give up just yet and continued experimenting, including Michelson himself, but they never could identify a luminiferous ether. But one of the scientists that tried to find it was French physicist Georges Sagnac. He had set up an interferometry experiment in 1913, which still failed to find the luminiferous ether. But he was able to find that there's an effect caused by rotation. It now bears his name as the Sagnac effect. So let me explain it briefly. If you have an apparatus sends out a light beam right here, and then you have a half-silvered mirror, which means half is reflective and the other half is clear. The light beam goes through here, it gets split, so half the beam goes this way and around, and then through the clear part again to reach a detector. The other half of the beam hits the silvered part and is reflected and goes this way around, bouncing off these mirrors in the corners, then comes back and reflects off the back of the mirror to the detector. So both light beams are going through the same distance, and if there was no rotation or anything happening to it, this apparatus, the beams would overlap exactly at the detector. But if there's any rotation going on, one beam will reach the detector before the other, and that creates a pattern that can be measured, and you can tell exactly how much rotation was happening to cause that effect, and that's the Sagnac effect. It would be 50 years before scientists used this knowledge to create a gyroscope that was better than the mechanical gyroscopes that had been already in use for decades. And the invention of the laser in the 50s gave scientists Masek and Davis a chance to produce the first ring laser gyroscope. So other technologies have developed too. So now, besides mechanical gyroscopes, we also have a ring laser gyroscope, the interferometric fiber optic gyroscope, which uses fiber optic rings or loops of fiber optic cable to increase the distance so it doesn't use mirrors. Then we also have electromechanical gyroscopes. There's the Coriolis vibratory gyroscope that has a small element that vibrates. And then we have the MEMS, the micro electromechanical system that uses very tiny parts that fit on a computer chip. Your smartphone has one of these in it. So ring laser gyroscopes form the core of modern inertial navigation systems, typically integrating 3 orthogonally mounted RLGs to cover the X, Y, and Z axes with triaxial accelerometers to enable dead reckoning computation of a vehicle's position, velocity, and attitude independent of external references such as global positioning system. But those work together as well. In commercial aircraft, the Boeing 777 has 6 Honeywell ring laser gyroscopes. The Airbus A380 has 3 ring laser gyroscopes paired with accelerometers. For military use, the Tomahawk cruise missile has RLGs because they are jam resistant and will reach their target. The F-35 Lightning II fighter jet has ring laser gyroscopes, as does in the sea the Virginia-class submarines by the U.S. Navy. In spacecraft, the Space Shuttle had ring laser gyroscopes. The Hubble Space Telescope that needs to aim very precisely at stars has one. And the Orion spacecraft that was used in the Artemis II program that took 3 Americans and 1 Canadian around the moon. The satellites and planetary probes also have them. They can withstand the vacuum of space and radiation exposure. Here's some ring laser gyroscopes in common use. Honeywell makes one for aircraft, but it covers only one direction, so they need three perpendicular to each other to make the X, Y, and Z axes. Then there's this gyroscope made by Kerfot, which already covers the X, Y, and Z axes in one device. Besides navigation, ring laser gyroscopes are being used in scientific research. The ring laser gyroscope plays a pivotal role in rotation seismology, enabling the detection of rotational ground motions induced by earthquakes that traditional seismometers often overlook. As an example, a team of researchers from the Technical University of Munich, TUM, and the University of Bonn, both in Germany, has succeeded in measuring fluctuations in Earth's axis using the high-precision ring laser at TUM's Geodetic Observatory in Wetzel, Bavaria. They will accurately measure the slight wobble of the Earth's axis caused by the gravitational pull of the Sun and the Moon, called nutation, and the length of the day. Another project in Germany is called ROMI, Rotational Motions in Seismology System. It's a multi-component ring laser gyroscope array with 4 orthogonal components installed at the Geophysical Observatory Fürstenfeldbruck near Munich, Germany, and operational since 2015. ROMI achieves a sensitivity on the order of 10 raised to the negative 10 radians per second, allowing it to resolve rotational signals from distant earthquakes and contribute to improved models of seismic wave propagation, helping us to better understand earthquakes. Another ongoing project is in Italy. It's called GINGER, Gyroscopes in General Relativity at the Istituto Nazionale di Fisica Nucleare in Italy. If you're Italian, let me know in the comments if I said that correctly. It's a proposal for measuring in a ground-based laboratory the inertial frame-dragging effect that is predicted by general relativity and is induced by the rotation of a massive source, and in this case the Earth. This will accurately measure Earth's rotational effect on the fabric of space-time. A prototype gyroscope called Gingerino has already been tested and shown promising results. One of the reports I looked at describing the Ginger project said when operational, it would be able to detect a rotation equal to the width of a human hair from 20 miles or 32 kilometers away. There are also ring laser gyroscope projects going on around the world in University of Canterbury in New Zealand and the Huazhong University of Science and Technology in Wuhan, China, among others. With all the accumulated scientific knowledge of over the centuries, you'd think that there's no doubt that the Earth is a rotating sphere and that it orbits the Sun. But there are some small number of people who want to insist that the Earth is flat and stationary. And there's a documentary made in 2018 called Behind the Curve that shows what happens when one of these groups of people actually took a ring laser gyroscope to try and prove that the Earth is stationary. So let's see how that went. We'll be looking specifically at a group called the Globebusters, hosted by Bob Nodell and Jaron Campanella.
We carried out an experiment to test the rotation to the Earth. If the Earth is spinning at one rotation every 24 hours, that means that every hour it has to turn 15 degrees. And if the gyroscope is mounted anywhere on Earth, it's going to drift. In today's 21st century navigation systems, they're using what's called a ring laser gyroscope. It is extremely precise. If we could simply get one of these ring laser gyroscopes, we would be able to prove once and for all that there is no rotation to the Earth. One of the people in the community actually purchased one for $20,000. But what we found is when we turned on that gyroscope, we found that we were picking up a drift, a 15 degree per hour drift. Now, obviously we were taken aback by that. Wow, that's kind of a problem, right? We obviously were not willing to accept that, and so we started looking for ways to disprove that it was actually registering the motion of the Earth and that it in fact was registering the motion of the sky. So the next thing that we set out to do was to encase the fiber optic gyro in what's called a zero Gauss chamber to see if we could actually shield the energies being generated by the heaven. And we were unsuccessful with that, unfortunately. So the next thing that we're going to try is encasing the entire apparatus in bismuth.
So let's sum up what this shows us about the Globebusters and flat earth believers in general. They came from a bias that says they can throw out decades and centuries even of scientific knowledge and come up with two proposals: that the earth is flat and that it's stationary. Then they thought they were so convinced that they were right that they could use the tools of science to prove their case, only to find that it disproved their case. It showed that the earth was rotating 15 degrees per hour. So what did they do? They denied the results. They put it in a gauze chamber thinking it would be magnetism would make a difference, or put it in a bismuth chamber to think that radiation would make a difference. And neither of those things worked. So the 15 degrees per hour was established by their own experiment. They just tried so hard to deny the obvious, and that is, they were wrong about the stationary Earth. Tragically, Bob Nodell passed away in 2023, but his co-host with Globebusters was Jaron Campanella, who went by the name Jaronism, and he continued to push the flat Earth narrative even after this experiment, but eventually he went to Antarctica and witnessed the 24-hour sun for himself and realized that that would only work if the Earth was a rotating sphere. So now he's left the flat Earth community and he's trying to debunk them as well. My question for him, if I ever met him, was why wasn't the ring laser gyroscope experiment enough to change your mind? Why did it take a trip to Antarctica? But it doesn't really matter because the science is sure of the results, and we don't need the Globebusters experiment to prove it one way or the other. Science is already very well established on that, and in fact, there's an international organization that keeps track of the Earth's rotation on a continuous basis and gathers that information from other scientific organizations and distributes the information to others that need it concerning the Earth's rotation and the length of the day. It's called the International Earth Rotation and Reference Systems Service, and it was established in 1987, and it's headquartered in Germany. And as you can see, it's a global reference for time and space. The IERS provides precise data on Earth rotation, reference systems, and geophysical fluids, together with related models and standards, essential for navigation, geodesy, astronomy, and research. So it's important for science to get this right, and they do. One other thing I'd like to leave you with is just how precise the Ginger project that I mentioned earlier in Italy will get. It has a precision they're hoping to achieve of 1 femtosecond, which is the second unit, to 10 to the negative 15th power. So that's 0.14 zeros and then a 1. They already have a level of precision where if there's a massive earthquake like what we've recently had in Venezuela, and in the last couple of decades Japan and Indonesia have had massive earthquakes, that it actually can affect the rotation of the Earth. And that's been detected. So that's how precise they already are, and this project in Ginger will be even more precise than that. So when you hear in the news that an earthquake caused a change in the Earth's rotation, that's been measured. So this video essentially completes a 3-part series on how the Earth's rotation was demonstrated and measured. We'll have links to the other 2 videos in our description. The first one was on Foucault's pendulum in 1851. The second one was on Foucault's gyroscope, which he did in 1852. And then this one was on advancements to gyroscopes, and especially the ring laser gyroscope. If you like this kind of content, be sure to like and subscribe and hit that notification bell. So we'll see you in the next Robinson Twins Present Earth is Our Spherical Home Planet.